Well, hello class. Let's take a look at an azide. And we have an azide which is N3 minus. And that azide can, when you look at its Lewis structure, looks like this. One, two, just like that. So I can draw it like this or expand it out like that. And when you take a azide, and the azides typically is going to come in a salt form like sodium azide. And if you take that sodium azide and treat it with a alkyl halide, and we can look at just a general mechanism here where we have a alkyl halide, and let's use bromine, since for some reason I always like to use bromine. And if you take those two reagents and react them together, overall, what are you going to do? You're going to do a SN2 mechanism in which the azide is going to replace the bromine. So you would have something like this. Or you could have rewritten it looking like this. And so that would now be 1. That'd still be positive. That would be neutral. Negative. Okay. Let's see here. Yeah, just like that. So the overall azide is neutral, but this nitrogen is positive, that's neutral. Now I want to make a big deal about something, and it's this guy right here. I'm just making sure it's recording. It's SN2. So you could have, let's say, a halide that looks like this. That one would work because why? It is a primary halide, alkyl halide. What if you have a secondary alkyl halide? Yeah, that could work because secondary alkyl halides undergoes SN2. But if you had a tertiary alkyl halide, will this reaction right here work? I hope all of you are saying no way, because you cannot do a SN2 mechanism on a tertiary alkyl halide. So I'm drawing you a generic structure, but note that you have 3 versions and only 2 of the 3 will work. So mechanistically, what's happening here is we could take the alkyl halide, and in my case, an alkyl bromide, and I'm going to expand out the azide, negative, and mechanistically, what is it? It's an SN2, so the negative charge, boom, boom, backside attack, kicks it off, and gives us our azide. And then minus here, plus charge. Now, if you just want the azide, then you're done. But the reason why we're making an azide is because we can take this azide right here and convert it into an amine. That's our goal. We've synthesized the azide so we can convert it into an amine. That's the whole purpose here, is to make amines. Now, how do we make that amine? Well, we treat that with lithium aluminum hydride. And then you have to do a workup, aqueous workup or acidic workup, doesn't really matter. And so you can protonate it. So then what's the next step then if we want to convert this into a amine? Well, if we take a look at lithium aluminum hydride, what happens is this hydrogen aluminum bond, we've seen it time and time again, come in an attack. And then that's going to go like that. So that's going to give us the molecule that I'm going to draw down here. That's going to give us a R, nitrogen. We just added a hydrogen. There's already a lone pair there. Okay. Still have that lone pair. Single bond nitrogen. You can't see that hydrogen down there, can you? So let's draw it like this so you can see it. So there's our lone pair, there's our hydrogen. Okay, and then you're not going to be able to see this. I'm going to have to expand this out. So let's start over here. So this arrow right here, this blue arrow, is going to give us this right here. Nitrogen. We're going to add our hydrogen. The one bond, lone pair, double bond right there. All right. So 1, 2, 3. Let's see here. Okay. Well, what's our overall product here? We only have one nitrogen. Right now we have 1, 2, 3. So we got to get rid of we have to get rid of 2 nitrogens. And so what you can do is take the lone pair, bring that down like so. And then this nitrogen bond right here is going to break. Okay, so we already have the lone pairs there. And when that occurs, what happened? We have our hydrogen still. That lone pair is still there. That lone pair is that guy. And then we have 2 electrons from that bond, which I'll put right there. And so that's going to give us a negatively charged nitrogen species. And then these 2 nitrogens right here do what? What's that? That simply is N2 gas, nitrogen gas. And so that bubbles away. And so now you have this amine that's negatively charged. And so then we do step 2 right here. We just do an acidic workup or an aqueous workup. If you just add water, water is good enough. If you add water to that, and let's maybe use a different colored marker maybe. All right. We'll just draw it over to there. If we just add some water, what's going to happen? We're going to have a proton transfer step in which we just come here, grab a proton, boom. Gives us to our product. Okay. Pretty straightforward. So if we clean this up a bit and just write an overall reaction. Let's clean this up. We can say if you take an alkyl halide and you treat it with sodium azide, right, that will get you your azide. And then you can treat that with lithium aluminum hydride, and that will give us that species. And then if you do a aqueous workup, you will protonate that and generate our amine. So overall, that's the process. All right. So the next reaction that we want to look at is a named reaction called Gabriel amine synthesis. So Gabriel amine synthesis is a useful reaction because it can make primary amines very effectively. Remember when we looked at trying to make amines with ammonia and then you make like a mixture of compounds? Well, with this molecule called phthalimide, if you take phthalimide and you treat it with potassium hydroxide, which is a strong base, and that base is going to abstract that proton, and it's going to give us this product right here. Oh, then there's already a lone pair there. And then that would give us water, and then our potassium spectator ion. So now what we have here is potassium phthalimide. Now if you take the potassium phthalimide and you treat that with an alkyl halide, and typically you're going to use a primary alkyl halide. Now you can use a secondary if you want. You cannot use a tertiary alkyl halide, but typically, generally speaking, the Gabriel synthesis uses primary alkyl halides. Can you see what's going to happen next? We will take this guy and do what? A SN2 mechanism. So that's going to generate this species. And we just put on a carbon like that. Now the halide, you can use chlorine, bromine, and iodine. Let's see, now we have that. Perfect. Now the next step, I'm going to show you two ways, okay? You can just add some acid, some aqueous acid. And what that's going to do is this looks like an amide. Remember the mechanism for hydrolyzing amides under acidic conditions? What does that do when you hydrolyze a amine? Well, it turns them into carboxylic acids, right? So what's going to happen is this carbon-nitrogen bond is going to be replaced with a carboxylic acid. And then we have this guy right here. It's kind of the same thing. So you generate your carboxylic acids under acidic conditions, and then what pops off? Your amine. And you will generate, so that pops off, plus you will have N, boom, boom, R, and you'll add a lot of protons onto that nitrogen because you're under acidic conditions to get a protonated amine. All right. Now, if you want just the amine, the unprotonated version, like that, what would you have to do? You just would have to add a little bit of base to deprotonate that, and boom, then you have that. But that's the overall goal here, is you're making primary amines using the Gabriel synthesis. Now the second way that we can do this, where do I want to draw this? So that's one way to do it, is with acid. Another way to do it is, instead of treating it with acid, would be treating it with hydrazine. All right. When you treat it with hydrazine, you're going to still get this product. All right. When you treat it with hydrazine. So let's take this piece right here, treat it with hydrazine. You will get that. You'll get the product that we want. But the reason why we use hydrazine is because when you treat it with this compound with acid, it just goes really, really slow. And sometimes people just don't have the patience for it. So they found if you treat it with hydrazine, it goes a whole lot faster. And then you just generate this species right here. Like that. And it really doesn't, this isn't what we're after. Who cares about that? We're after the amine right there. But that's the difference between hydrazine versus aqueous acid. It gives us a different product here, but we don't care about that piece because we are after the primary amine. All right. Okay, the next reaction that we're going to use and look at is reductive amination. And this is really big in the protein science community, but organic chemists use it as well. It's just another way to make amines. So before we talk about reductive amination, let's review some things. To recall, if you take a ketone or an aldehyde and treat it with ammonia with a little bit of acid, that's going to generate that is a nitrogen H. It's going to generate the amine. And then you could treat that amine with lithium aluminum hydride and some water. And then you would generate your amine. That's one, recall that, and still need our R group there. You could also use another reducing condition. So you could take this amine as well, but you could treat it with some different reagents. Let's say if you treat it with some hydrogen gas and some palladium right there. That will generate the same amine as well. I misspoke. That's not palladium. That's platinum. Okay? Palladium is PD. PT is platinum. So that's another way that you can generate a amine. But we can now introduce something different. And that's when you take a aldehyde or ketone, treat it with ammonia, and then you're going to throw into the mix is you're going to have a little bit of acid present, and then you're going to have the reduction piece also in the reaction. And the one that we use looks like this. So you remember sodium borohydride? It looks like that. Well, don't use that. What you're going to do is actually use sodium. You still have the boron. You still have 3 hydrogens, but you replace one of the hydrogens with a cyano group. And that guy is called sodium cyanoborohydride. So that's the one that you're going to use, not that one. I just drew that one so you can see the relationships here. So now what is the advantage of this? Well, do you see how we have the same ketone or aldehyde, but now we are in one reaction. All 3 components are in one reaction. Instead of up above, right here, we have to do it in 2 or 3 steps to get us to our amine. But this way, it's just done, boom, one pot. We call it a one-pot synthesis. And when you treat that aldehyde or ketone with these 3 things all in the same pot, you will generate your amine. And that process right here in orange is called reductive amination. And that's really, really important. One thing to notice is when you look at sodium borohydride, we have 4 groups. And then when you look at sodium cyanoborohydride, what does it look like? We already briefly talked about it. I'm drawing this out because I want to show you something. We have replaced this hydrogen with a cyano group, and this cyano group is electron withdrawing. And so that, because it's so electron withdrawing, it is going to help stabilize that negative charge. And that negative charge now is going to be less reactive. And so cyanoborohydride, we can use it more selectively. Okay? And what I mean by that is if I took a aldehyde or a ketone, well, let's look at it this way. Let's do this little stepwise here. That will help us see what's going on here. And then we can come back to the different reactivities here. And I think that will be the better way to do it. So we have a generic aldehyde or a ketone. When we treat it with NH3 and some acid, and then sodium cyanoborohydride, okay. The first thing that happens is the acid and the amine generates the amine. And then once you form the amine, the sodium cyanoborohydride will reduce the amine into the amine. Right. So this is all happening in the same pot, same reaction, but the reaction does go stepwise. It's first generates the amine, then this reducing reagent gets it here. Now, if we try to do this reaction with sodium borohydride, right. So if I try to do it the same ketone or aldehyde with ammonia, with some acid, and then sodium borohydride, what will happen is sodium borohydride is more reactive. And so we will not generate the amine. This sodium borohydride is just going to quickly reduce the ketone into an alcohol. And then that's just not what we want. We want the amine. So we don't use this because it's just too reactive and you can't control it. And because it's so reactive, you don't form the amine. You form an alcohol. But because sodium cyanoborohydride is less reactive, it is also more selective. And so this species right here does not reduce ketones or aldehydes very well, but it does reduce amines very, very well. And so this right here is not going to touch the ketone, so that leaves these two reagents right here to do its magic, form the amine, and then the sodium cyanoborohydride reacts with this to give us our amine. Fun stuff. All right. Another cool thing to take a look at is, I'm going to give myself a little bit more board space here. Okay. Is what if we don't use ammonia? What if we use a different type of amine? So let's say we use NH2 like that. So a primary amine. What would our product be? We would get, and then an H and an R. I'm not drawing the geometry very well, but we generate a secondary amine right there. Okay. So we start with what? A primary amine. We use it to generate a secondary amine. We could also use a secondary let's see here. Now you can also treat aldehyde or a ketone with a secondary amine. When you treat this with a secondary amine and these conditions under reductive amination conditions, what would we generate? We would now generate a tertiary amine. So I would highlight that. That's a really important way. How to make tertiary amines is by reductive amination, which is pretty slick. Okay. Okay, so let's clean up this board so we can start talking about the next topic. Now, we have already previously discussed this concept of acylation, where if we take an amine and treat it with, let's say, Cl, like an acid chloride like this, and you see that we have what? 2 carbons. Okay. Let's see here. If we have a primary amine and we have an acid chloride, and in this case, acetyl chloride, what are we going to generate? All right. Do you see how we put an acyl group onto the nitrogen? So we acetylated it. Now, why do you want to do this? Well, there's a couple examples where I can show you why acetylation would be a good thing. Because what if we have aniline here and we wanted to add bromine at the para position? Okay. What's going to actually happen? This is an activator, so it's going to be really, really reactive, and you are going to generate this. But we wanted this compound. So this is a problem. So how can we circumvent that problem? Well, acetylation or acylation can do it. So acetylation is when you attach two carbons, okay? Because that's from acetic acid, acetyl. So that is a specific type of acylation. Acetylation is acylation. But remember, a acyl group is just simply tacking that piece on. So we could tack on other carbon chains off of this carbon here, and that would be a acylation. Okay. Okay. So how does acylation help us out? Well, what we can do is, instead of doing the bromination, what if we do an acetylation first? And when we do that, what would we get? We would get our aniline derivative here. That looks like that. Now this species is not a strong activator, it's a moderate activator. And so now you can do your bromination, and that will favor our para position. And then you can just take that guy off. That's an amine, or sorry, an amide. And we've seen it if we take some water and some acid, we could hydrolyze it. We've also seen that if we, or we could just do it under basic conditions. Either or, that would hydrolyze the amide into our product of interest. So acylation helps us to overcome this overbromination or polybromination problem. It's kind of cool. Another thing that you need to be aware of is that when you are dealing with aniline, you have a nitrogen atom that's pretty nucleophilic. So if you wanted to do, let's say, a Friedel-Crafts alkylation, it won't work. So let's just say we we're envisioning something like this. Okay, and we want to do our Friedel-Crafts alkylation reaction. So we are expecting to get this product right here, right? That's what overall, that's what we want to have happen. But that's not going to happen, right? Because there's going to be competition. Because typically in the mechanism, it's the chlorine that comes in and attacks that the iron, and it coordinates it with it. But guess what? You also have this amine that can also do the same thing. And so when the amine attacks the iron, what do we have here? H2 is going to attack the iron. Okay. Double check something here. That would be positive, that would be negative, right? And now what has happened? You've now turned the ring in. This species right here is now a deactivator. And you can't have deactivators on the ring to do Friedel-Crafts alkylation. So aniline with Friedel-Crafts just doesn't work. But what if you really, really, really want it and need it? What if you have this as your target and you need that aniline? Well, one way to help us with this problem is acylate it. So we could take our aniline, if that's our compound, we could treat it with our acetyl chloride, and that's going to give us that compound. Then this is what? That is a moderate activator. So we can do our Friedel-Crafts alkylation. That's going to go para. And that's getting cut off there. So we'll add our methyl group there. So what I'm circling right there, that's our methyl, our CH3. Can't really see all of it. And then what would we do? We then would treat it with some acid or base to hydrolyze the amide to get us back to our target compound right there. So acylations help us circumvent problems. And I just showed you two problems that we can encounter. Okay, this next reaction is a lot of fun, in my opinion, because it's going to bring back some reactions that we learned in Orgo 1. So it's a good reaction to help us review Orgo 1 material, but then learn something new at the same time. In a Hoffman elimination is where we have an amine and we treat it with three different processes. We treat it with like excess amount of methyl iodide. And then we take that and treat it with silver oxide. Let's actually draw it right. Let's see here. silver oxide would be that. And then the third one, we would add some heat. And when you take those three reagents, treat it with the amine, what do we get? We get an elimination. And our product looks like this. We get a terminal alkene. So when we look at the starting material, look at our products, we have eliminated a nitrogen atom and the hydrogen's attached to it. That's popped off. And we've generated a terminal alkene. Why did we not generate a more stable internal alkene? Because that is di-substituted, that is mono-substituted. So why does this reaction give us this guy instead of this one? So what we can say is that the Hofmann elimination reaction is going to give us the less stable alkene, which we could just also say, excuse me, the anti-Zaitsev's product. Remember the Zaitsev's rule? Let me write that down. So this is the spell this right, Zaitsev product. Recall from the Zaitsev's rule that when you do an elimination, the Zaitsev's rule says you want to form the more substituted alkene. But in a Hofmann elimination, we are generating a less substituted alkene, so it's called the anti-Zaitsev product or Hofmann product. So what's going on here? So in the first reaction, you can see that you have a nitrogen, which is very nucleophilic, and then you have methyl iodide. So you can envision a very simple SN2 mechanism here. That's going to come in and attack and kick that off. And so what's that going to give us? NH with a methyl group, right? And so that's going to happen over and over and over again until you have made the species look something like this. So you do that same mechanism that I've shown right here until you do it a total of 3 times. So now you have CH3, CH3, and CH3. So now we have a quaternary amine. So that's the first step. All right. But there we have iodine. So what do we have? There's a lot of iodine floating around as well. So that negative charge and that positive charge, they're going to associate with one another. And so we would have quaternary ammonium salt. All right. The next step, so that's the first step we get here. So our second step is we're adding the silver oxide. And the silver oxide is simply just replacing the iodide with a OH. So let me show you what that's doing here. So this silver oxide is going to react with this to give us silver iodide. And then it also generates, it also generates hydroxide. So that's its whole purpose, is you add this, it reacts with the iodide, gives us silver iodide, and then It generates hydroxide. Now the hydroxide then is going to be used as the base. And we're going to do an elimination. Now what's interesting here is that amines are horrible, horrible leaving groups. But when we treated it with excess methyl iodide, what did we do? We make the quaternary ammonium salt. Now this nitrogen atom is a good leaving group. And so what we see here is that we have a proton there and a proton there. And I've already shown you the product. It's the alkenes right there. So that's telling us that the hydroxide here is going to abstract proton 1. Grabs the proton 1, adds the 2 electrons there to form the double bond, and then makes that leave. So now we have that as our product plus our amine. CH3, 3 of them. Okay, so that's a C right there, or methyl. There's 3 methyls. So it begs the question then, I've already told you the answer, that it's an anti-Zaitsev product. But why? Why does this hydroxide right here not come and abstract proton 2? The best way to answer and explain that question is by looking at some Newman projections. So before we get to the Newman, let me just clarify one thing. So step 1 gets us to get the quaternary ammonium salt. Step 2, the silver oxide, is to just replace the iodide with an OH. That's step 2. And then step 3, by adding the heat, allows the hydroxide to come in and do the elimination. So when we do this elimination, what mechanism am I using? That is a E2 mechanism. And remember, there's a very important rule with E2 mechanisms. The hydrogen being abstracted and the leaving group that's leaving has to be anti-periplanar. If they're not anti-periplanar, does not work. So when we draw a Newman projection of this guy, we're going to see something very interesting. Okay? So let me draw the Newman projections and then we will talk about it. Okay, I have my Newman projections here. So what I'm going to do is I drew the molecule like this, and I've numbered the carbons. And I'm going to look down from this direction, down the carbon 2 and carbon 3 bond. And I'm going to draw what I see. And right now we have this methyl group and the big quaternary amine gouged to one another. And that's not going to be very good. Why? Because of sterics, right? So we can rotate around that bond and give us this Newman projection right here. Now, this one's going to be the more stable Newman projection. Why? Because now we have the methyl groups here, this methyl group right there, anti from the amine. That's the most stable. But in order to do the elimination, this hydrogen right here on carbon 3 has to be anti-periplanar. And that's what we see in this conformation right here. This hydrogen and the leaving group is anti-periplanar. That's the requirement. But in that conformation, it is so unstable due to these big groups gouged to one another. So this is the more stable conformation, but in this position, there needs to be a hydrogen. That's because it needs to be anti-periplanar so it can leave. but there's no hydrogen there. So this process right here, up, so the top Newman would give us this product right here. It would given us the more substituted alkene if we went this way. That's what you would expect, but it doesn't happen. The Hofmann elimination is anti-Zaitsev, and the reason now is if you look down carbon 1, down carbon 2, now this way, looking at it, what do we see? We see the leaving group and a hydrogen anti-periplanar. So this is the more stable conformation, and we have the hydrogen and the leaving group anti-periplanar. So this hydrogen right there is that hydrogen. And so when it does the elimination, so if we had our base right here, I was going to come grab that, go right there. It's going to be anti-periplanar and be easier to do. And it gives us that as our major product. Pretty slick. Okay, that is, I'm out of time now. Let me just take another look at one more thing, make sure I'm not missing anything. Okay, we'll stop there. If you have any questions, let me know.